Okay, so we've got lab tomorrow from 10 to 12. And some of you who have not had a chance to come to lab and don't want to wait till Monday should come, as long as we can fit all in. Is anybody from the Monday group planning to come tomorrow? Okay, that should be good. Also, it's better for you to bring your own laptops with Nova loaded on to use that. We can use the desktops in the lab. Last Friday, there was a problem with the licenses, and we, instead of having a general license for all those laptops on the server, we had to set up so that people could run individual licenses on those machines, and we did it for a few machines. Now, the guy who is in charge of the lab has been working on trying to install the license on the server for all the machines, and there have been some problems, so hopefully it will be solved today, but I don't know. So if you come tomorrow and you don't have your own laptop, then we just have to make sure that you can download a license onto the machine you're working on in the lab. It worked last week, but it does take a few minutes to do, so it's better if we have that problem solved. Yeah. Yeah. So, unfortunately, as I mentioned, there's bad timing, so that the Monday group are cheated out of 2 labs. The labs are not kind of very tightly organized, so, there's lab 1 on week 1, lab 2 on week 2, and so on. In the labs, what we do is we help you towards the coming up work set, of which there are 10 work sets. So you'll see the way the work sets are scheduled. Basically, we've got the slow startup, so your first work set is only due Tuesday a week. But please start it right away this weekend, or certainly beginning of next week, and don't wait until Monday a week and then try to do everything on one day, because then it's going to be difficult for us to help you. And then you'll see that there's some relief in terms of a work set when you have your midterm. There'll be a gap in the work sets then. And then as we approach the end of the year, I space the work sets out so that you don't have to do a work set over Thanksgiving, and you get the work sets done in good time so that you're not trying to hand in a final work set while you're studying for your final exam. So that's why we have 15 weeks of class, but only 10 work sets. Okay, any other questions about that? Yeah. Yeah, it's in 124 Mulford. And Colin's going to be taking it tomorrow. I don't know if Eric's going to turn up or not. But you'll take it on the Monday. Okay. So some of you will only arrive on the Monday, but that still gives you a big chunk of time, 8 days, to finish the work set. Anybody finished it yet? Slackers. Jeez. Okay. So in the last lecture, and the reason why I got this up is this is being videoed and voiced from, but there's no video camera on me, so only the media material comes from my laptop and from my voice. I'm just going to leave this up. I'm going to work in this part of the board, and I'll come back to this later. But I know that when I'm doing board work, you pay more attention than when I'm showing stuff. Is this true, or is it just a false assumption? Okay. So anyway, I think there's better communication if I'm talking directly to you rather than reading stuff up there. But that's up there at the moment. And again, if you go to the B Space website, this material here will be called Lecture 3, and you'll have it there if you need to go through it. So we were talking last time about discrete models. And discrete model taking the form x at t plus 1 is some function x of t. And we looked at a model that we call the generalized Beaverton-Holt model. And when we looked at solutions to this model, what did we notice? Was there anything that you thought, wow, I didn't realize that? Not. What do you guys think about when you're not in this class? Having a good time? These are very important questions to your lives. Yeah? Uh-huh. Okay, and how does that affect solutions? Right, but were you surprised at the nature of the solutions? Okay, so some solutions just kind of rose fairly rapidly and then gradually and then asymptoted out. Some gave you oscillations that were periodic, and some gave you chaotic behavior. So in fact, that was kind of unexpected, and it was unexpected if you study dynamical systems processes through using the other kind of model, which is the differential equation model, where we say dx dt, the rate of change of x with respect to time, is some function of x. And because we're saying x changes with time, you can say it's some function of x, but we implicitly know that x has got to change with time, so we could write it this way or this way. And if you have a look, sometimes we say dn dt equals f of n. Sometimes we use an x, sometimes we use an n. You'll see that when we talk about models where we're interested in biomass of the population, we often use x. And when we're interested in numbers, we often use n. Now, a model like this says that n changes continuously with time. So how can numbers change continuously with time? Can you go from 27,100 individuals to 27,100.5 individuals? Can that happen? Well, of course it cannot. Unless you want to count yourself as half an individual for some reason. But since none of us like to do that, these are all integer values. So you can see right away that this is kind of an approximation. However, if we measure n as a density, so for example, if we're counting mice in a field, and we say how many mice per acre, then you can get 2.3 mice per acre. And so if you've got tens of thousands of acres. So this reminds you that it's an approximation, and if n stands for numbers, typically we think of n as standing for densities rather. But we do have models, discrete models, where n can only change discretely. And you've got to discriminate or distinguish between discrete changes in time and discrete changes in the space. So far we haven't talked about discrete changes in the space. All our state variables have been continuous. But we just keep this in the back of our mind. Okay, so we talked about this type of model, and we found that we can get asymptotic behavior, cyclic behavior, chaotic behavior. Now we're going to look at these kinds of models, and it turns out that these models actually behave much more regularly, which is one of the things about continuous models, is that n, it turns out, for a model like this, you can't get this chaotic behavior. And we can talk about why that might happen later. But what we're going to do is we're going to come to a model like this, and we're going to start building simple population models out of elementary concepts. So if you have a look at a population, and I'm just going to use X in this case for a measure of the population. It could be the biomass or it could be the numbers, but we'll think of it in terms of numbers. So what kinds of processes can change the size of X in a population? So population models are called demographic models. Yeah? Yeah, exactly. Yeah, so birth, wow, gave me everything. Death and net migration. So net migration is immigration and emigration. So these are the simple demographic. Anybody here been a spelling bee champion? Anybody participate in spelling bees? Okay, so you know what the root of the word demography, where it comes from, what it means? Anybody? Yeah, so demos is a Greek root meaning the people. So these are processes involving people, and then there's other processes that we'll talk about later in the class that we call epidemic. And anybody know what's the root of the word epidemic? Epi is what? What does the word epi mean? Yeah? Right, okay, so it's around the population, or sometimes upon the population. So that imposed on demography are processes that we call disease. Now, disease, of course, affects your death rate. So epidemics affect demography through the death rate, but we'll come to those kinds of models later. So how many of you have been following this Ebola outbreak? Anybody have any comments or views about it? Do you think they should be bringing the American healthcare workers back to the United States for treatment? What do you think? You can have a view on either side. I mean, it's pretty dangerous, isn't it? You bring an individual here, you take them to a hospital in Atlanta, say at Emory. Some healthcare workers pick it up, they go home, they give it to their kids. Their kids go to school. Somebody flies over to San Francisco. Somebody, yeah? Yeah.
Not airborne, so if you're flying someone over here, we do have the dedication and like the built technology to keep them at the hospital. Their healthcare workers are being like getting illness are from the third world,
yeah.
And they are working in less than conditions. I don't think there's very much risk.
Yeah. So the important point is how is it transmitted and the transmissibility. And unlike respiratory diseases like SARS, which can be transmitted more easily by people coughing, Ebola is much more contained. And so people feel more confident as long as everybody takes extreme precautions, which they have been doing. But certainly if you watch the news, you'll get both points of view. And people who make an argument on either side have a point of view, and there's a particular legitimacy to both points of view. So it depends on your ethics to some extent. Like, do you help people while taking a risk yourself, or do you totally minimize your own risk and not help people? This is just an ethical decision. It's not a right or wrong. Okay, so what we talk about here is per capita rates. So birth per capita rate. And so we'll have a parameter B and a parameter D, and that's a death per capita rate. So if we're going to build a model, what do we mean by per capita? Okay. Yeah, so we're talking about rates applied to individuals. So to get the total rate, we have to multiply by the number of individuals. Or if it's biomass, it's the rate per unit biomass. So sometimes we'll deal with like fisheries models. We'll talk about the growth rate of a population per unit biomass in the population. It's like if you say how much weight does an elephant put on each day while it's growing, you don't really care whether it's, or if you say it puts on 10 kilograms a day, that doesn't mean much to you. What's more important is to say its size is growing 1% a day or 0.01% a day. So relative to its current size, how rapidly it's growing. That's kind of more meaningful. And so you have to get the total growth rate, you have to multiply by x. So if we do that in the context of dx dt, so we say dx dt is equal to, now it's growing at a rate b times x. Now again, when we say this, we're averaging over the whole population. So some individuals are giving birth and some individuals are not giving birth. But on average, the rate at which newborn individuals appear is b. But you have to choose your units of time. So whenever you have a model like this, you have to say, what are my units of time? So in a population growth, what do you think are good units to have for time? Annual rate. So like for humans, we always talk about an annual rates. But if you're looking at mosquitoes, and you want to know how's the mosquito population growing in the summer, and you need to know that because they may be carrying a new virus. Anybody know of an emerging virus that mosquitoes carry? Yeah? Okay, dengue is one. Any others? West Nile, right. Any others? Malaria, okay. So should we be worried about malaria? The answer is yes, because there are mosquitoes in California, in the Delta, that carry malaria. And then we get immigrants from other countries who may come in with a malarial parasite. And so occasionally you do get an outbreak, but it's pretty much under control. And in California we also have mosquito control districts that control mosquitoes, but there are a lot of places where there isn't control. So we have what are called these emerging neglected diseases or emerging pathogens. Some of them are, if you have a look at the whole healthcare industry and you look at drug companies love to make drugs that are used for heart disease. And that's because we have all these old people like myself, and potentially we can have heart disease. And so there's this huge market, and we're all relatively wealthy, and we can pay hundreds of dollars a month for these drugs. And so it's a great market. But for example, Ebola, why isn't there a vaccination for Ebola? Why isn't there a drug to treat Ebola? Well, that's one of the reasons. So there's no huge incentive. The private companies are not doing it. So what happens is the National Institutes of Health and their scientists, and the scientists they support at universities, they have to have programs to encourage people to develop these drugs for so-called neglected diseases. And in a way, this is why the free market doesn't work particularly well. So hear all this stuff about the free market. Leave it to the free market. Well, the free market has limited capacity, and they're going to prioritize. And I guess if Ebola does really get to be a problem, then they'll all scramble to make money out of it. But for the moment, they're looking at the next drug to control cholesterol or something like that they can sell to hundreds of millions of wealthy Americans. Okay, so we've got dx dt is equal to bx, this is the birth rate, per capita birth rate, minus dx. And very often when we study a population process, it's so difficult to actually characterize these migration processes that it's easier just to draw a boundary and to say the net migration is 0, the first approximation. So many of our models do that. Now, of course, if you're a demographer and you're building models of the California population and you're making and you're making predictions, you're not going to do very well if you just say, okay, we'll count births and deaths in California and we won't look at how many people are coming in or going out. You're going to get it totally wrong. But if you look at a population that has boundaries that you can reasonably say the net migration is 0, then a model like this would apply. And so we can write this down as dx dt is equal to b minus d times x. And this b minus d we'll call r, and sometimes that's called the intrinsic growth rate, or the intrinsic, or the net per capita growth rate, or there's different names that it's been given. And that's the simplest model that you can have in a differential equation. And in fact, it's so simple that we can actually solve it analytically. So if we say dx dt is equal to r times x, now must r be positive or can it be negative? Yeah, so in this case, it can be negative. If we had to write down a population model, x at t plus 1 is r times x of t, and we discussed that last time, can capital R be positive or negative? Okay, so the key value for r over here is that if r is greater than 1, the population will grow. If r is less than 1, the population will decline. So if r is 0.95, the population is declining by 5% each time step. Here, if r is positive, the population will grow. And if r is negative, the population will decline. So you see that these are fundamentally two different kinds of descriptions of processes of change. And so you have to keep that in mind, because we're going to use both discrete and continuous models. And this is why when you use NOVA, you have to tell NOVA, is this a discrete model or a continuous model by checking that box, yes? Okay. We have a value x. We start out at x0. And for example, if r is equal to 1.1 and x0 is equal to 100, then if we calculate at x1, we'll get x1 is equal to 100 times 1.1, which will be 110. If we calculate, if r is equal to 0.9, then x1 would be equal to 90. So here we would be growing by 10%, and here we would be declining by 10%, yeah? Right, so in this one, r can't be less than 0, because then we'll get a negative number. Yeah, r can be positive or negative, because this is a rate of change. This is an actual value. So how do we get an actual value from a model that informs us about a rate of change? So this is the great mystery. How do we do this? Well, it's not that much of a mystery in the sense that we never wrote it down like this until the calculus was invented. And when the calculus was invented, then these descriptions became legitimate, and the way to solve them was developed by the methodology of the calculus. So this tells me that the rate of change is specified, and this tells me that the next value is specified. So this is a next value equation, and this is a rate of change equation. Well, so discrete means jumps, and continuous means you're changing continuously. This one's jumping on the interval. Here's time. I've got time at 0, time at 1, time at 2, time at 3. So I start out with a given number, and then I can calculate the next value, and the next value, and the next value. And you can see that I'm jumping along in time. So this is discrete in time. You can also have a discrete or continuous state. Here the state is continuous in that if I then take x1 and I multiply by r, then after this I'll get 81, but then after that I'll get something with a decimal point in it. So if it's discrete, then it can only take certain chunks of values. In this case, we might say we can only allow integers. If we could only allow integers, then it would be discrete in state. But we can allow any value for x, so that's continuous in time, but time itself is discrete. When time itself is discrete, the model tells us how to calculate the next value. When time is continuous, and we talked about that Greek, Achilles and the rabbit trying to catch it. And if you treat that as a discrete problem, it can't be solved. But if you treat that as a continuous problem, then an Achilles can run continuously, and over an infinite number of smaller and smaller intervals that add up to a finite interval, Achilles can actually overtake the rabbit or the tortoise. And so a continuous solution, we start out at a particular value, and then we can trace it continuously like that. So we can look up any value, like what's the value at 3.76521? And there'll be a point there that we can look up. Because it's changing continuously over time, there's a point we can look up. Yeah, if we say what's the value at 2.5, there's no value at 2.5. And the model will not be able to tell you what it is, because it doesn't know how to describe it.